Warning! The video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is a continuation of a series of videos in differentiation for Calculus 1. We are past learning about all the differentiation techniques and derivatives of functions, and now we're into the specialty topics. We just finished related rates, and now we go into the next natural evolution of topics, which is linear approximations and then differentials. Now, I like to start my discussion about linear approximations with this simple question. Suppose we're given a function f. What is the equation of the tangent line to this function at a comma f of a? Now I'm going to go ahead, I didn't tell you what the function was, so I'm going to go ahead and graph out some random function as a terrible x-axis, by the way, I apologize about that. And let's pretend as though this value right here is a. So therefore, the point is a comma f at a. Now, we have been dealing with tangents for such a long time that it's pretty easy for us to know what to do when handed a tangent line, and we know what the tangent line says. I'm going to go ahead and just draw a tangent line approximation in here. Let me just get a little bit better of our approximation there. Maybe something like this. That's good enough for me. And so you can see that would be our tangent line if we could find its equation, which we can. So let's go ahead and find out what the equation of that tangent line is, and then we're going to discuss what we're going to do with it. So let's see, to find the equation of a tangent line, you need two things. Because it's a line, you need a point, and you need a slope. Well, the point is actually just a comma f at a. And the slope of the tangent line at that point is the derivative at a, as we already know. So the slope is f prime at a. Therefore, the equation of that green tangent line, which I will go ahead and write the equation in green as well, is y minus the y value f at a. And that's going to equal the slope, f prime at a, times x minus a. And I could solve this for y to get the kind of the point slope version of or the slope intercept version of the line, but I'm going to slightly adjust it. I'll call it positive f of a and then plus f prime at a times x minus a. Now, of course, that's actually not, it's written in the opposite order that you normally write it. Normally you would write it mx plus b, and here we're writing it as b plus mx, but that's okay. That's not that big of a deal. That is the equation of this this tangent line for this arbitrary point on this arbitrary function. Now, the point of this section that we're going through right now is if somebody hands us a really, not terrible, but just a function, and they say, I need to know the value of that function, not at a, but at a point near to a. So let's say they want to know the value of the function at some uglier value than what a is. So let's pretend that a is a pretty point, like 1, 2, 3, or something like that. And they want to know the value for our function at, let's just say, x sub 1. So that value, the true value of the function at x sub 1 would be, let me zoom in here as much as I can, would be that blue dot right there. That would be the true value of the function. It would be x sub 1 comma f at x sub 1. That's the point. The value is f of x sub 1. However, if that's an ugly enough point, the x value that is, it might be much easier just to plug in x sub 1 instead into our tangent line. If we do that, notice that its value would be approximated, well, that's a terrible dot, so its value would be approximated using a tangent line right there. And that tangent line, we'll go ahead and call that tangent line rather than y, because I think that that's going to get a little confusing. We'll call that L for line. Okay. So that tangent line, we could approximate the value of f of a using, f at x sub 1 using L at x sub 1 instead. And because it's a line, it's much easier to compute than with, let's just say, a trig function or a combination of transcendental functions. It's just much easier to approximate the value of the function using the linear, the equation of the tangent line than it is to use the function itself sometimes. And that's the whole point behind what we're going to be doing in this video. We're going to use tangent lines to get approximations of functions at nearby points. And so some people will call this tangent line approximations. And they would be absolutely correct, because that's what you're doing. You're using a tangent line to approximate a function. Other people will call it a linearization of your function. You're basically flattening out your function a little bit locally and saying, well, locally, our black curve there is very much like the green line locally. Obviously, there is some error between those two when you get far away from where you built your tangent line, like this error right there is pretty bad. But if you're close to where you built your tangent line, then you can approximate values near to that. So let's go ahead and actually see the true definition here. The function L of x, which, remember what I did in the last page is I actually titled that y, that tangent line, as L of x. So I did that on purpose because that's what we're going to call our tangent line, is L of x. It's called the linearization of f at a. So L of x, and that's just our tangent line equation at a, is called our linearization. So let's see how this is used, because it is actually a very powerful technique to evaluate functions that normally we could not evaluate. And this leads to a bigger technique that's used in Calculus 2 called Taylor and Maclaurin polynomials, or Taylor and Maclaurin series. Very, very important polynomial expansions in the long run. All right, let's go ahead and just consider this function. F of x is equal to x raised to the 1.837 power. Terrible looking power, right? And you want to evaluate that function at 1.1, 1.01, and 1.001. Notice what I'm doing. I'm saying we want to evaluate that function at values nearer and nearer to 1, just to showcase that this is going to be easy to evaluate by hand, actually. And I've told my students about a technique to approximate roots of functions and stuff like that. So this topic goes kind of hand in hand with that. All right, let's find the linearization of f at 1. And that basically means, so when you read that, you might get a bit intimidated by that statement. Don't. It just means find the equation of the tangent line at 1. You can replace those words with that. That being said, let's go ahead and do it. So to find the equation of the tangent line, we need two things, a point and a slope. So the point's pretty easy here because we're going to plug in 1 to our function and we'll get out an output. And of course, that's pretty easy, right? Because you plug 1 into this function, you'll get an output of 1. That's our point. The slope, on the other hand, we need to find out what f prime of 1 is. Right? That's the equation of the tangent line. Is you need the slope of your tangent line at 1 will be f prime at 1. So let's find out what f prime is first, and then we'll plug in 1. Let's see, you bring down the power, so 1.837. Reduce the power by 1, and that is our derivative. And of course, that implies that f prime at 1 is 1.837. All right, so now we have our slope, we have our point, so our equation of our tangent line should be somewhat easy to find. So tangent line equation is going to be y minus the y value of 1 is equal to the slope, 1.837, 1.837 times the x value minus 1. Now, I highly recommend that you do not distribute out that right-hand side. Again, I'm going to write that in red right there. Do not distribute. The reason why will become apparent in a few moments. It's just very important for me to state that. The other thing I'm going to do is go ahead and just solve this for y, so that will imply that y is equal to 1 plus 1.837 times x minus 1. That is the equation of the tangent line. And in fact, what we're going to do is call that L of x. That's our tangent line. So there we go, 1.837, x minus 1. All right. And we know that the tangent line, just based on our first example in this video, the tangent line is a pretty decent approximation to the function near to where we built the tangent line. Again, going back to that page here, the tangent line in green is an incredibly decent, I don't know if those two words go well together, but it's an incredibly decent approximation to our curve f when you evaluate the line locally or near to where you built the tangent line. So using that logic, we should be able to approximate this function x to the 1.837 power near to where we built this tangent line using a tangent line. And we built this tangent line at the point 1, 1. So we should be able to use that tangent line to help us approximate f of 1.1, f of 1.01, and f of 1.001, again, because those are close to the point where we built the tangent line. So let's do that. Rather than grabbing a calculator and computing this, let's use a line. So f of 1.1. Well, that is approximately our tangent line at 1.1. And our tangent line at 1.1 is 1 plus 1.837. And we're plugging 1.1 in for x. And now you should probably you should probably see why I'm saying do not distribute that 1.837 to the x and the 1 there. Is because when you plug something in near to 1, the math is very, very simple. We're just going to move that decimal place over by 1, and this becomes 1.1837. Again, 1/10 times that 1.837 is going to be a 0.1837. Add that to 1, it's 1.1837. Now, before I check how close that is to the actual value, let's compute the other two, which were, let's see, f of 1.01 and 1.001. And let's see if those are any harder to compute. F of 1.01, again, we're going to use our tangent line approximation. This is such a cool idea. I think that it's really neat that you can just do something so simple as using a tangent line to help you approximate the value of a function rather than using the function itself. And a lot of people don't really understand how powerful this is until they start dealing with ugly functions. And you say, I don't want to deal with that ugly function. I'd rather deal with something that's much nicer like a linear function. And that's what we're dealing with here. Let's see. Now this will be 1.01837. And you could probably guess what the next value is going to be. F at 1.001 through the mathematics there, ... is going to be 1.001837. Now, I would like to compute this to see how accurate this is. So here I am at Desmos, and I'm going to go ahead and just type in the function itself. The function was f of x equals x raised to the 1.837 power. And we were asked to evaluate this function at, or approximate the value of this function at 1.1, and then 1.01, and then 1.001. Now, I want to just state it out loud. The values that we got for 1.1, That value was 1.1837, and we're within 1/100th of that. The real answer, you could see it here, is 1.19. Our approximation for 1.01 was 1.01837, and we have the true value 1.018 and then 4. So we got to exact out to 3 decimal places there. We're only off by 3/10,000ths of a unit. And then finally 1.001, we see the true value is 1.001837769. Our value was 1.001837, and then it stopped. So that's pretty decent for a linear approximation. And you can see those values here. So really, really close approximations just using the tangent line. Now let's go ahead and continue this idea of using a linearization to approximate a function. In this case, they hand us a function, and by the way, it's not always going to be the case that you're handed a function, and we'll see an example like that in a few moments, but for right now, we're kind of keeping with that theme of being handed a function. So let's suppose that we're handed this function 1 plus x to the negative third power, and then somebody says, hey, I need to approximate 1 over 1.1 to the third power. Well, that can be done using a linear approximation of this. If you notice, this function is 1 over the quantity 1 plus x, although that's a plus x to the third. These structures are very similar. So what I'm going to do is do a linear approximation to f, not at 1. This is what throws a lot of people off. A lot of people think, oh, you're going to do a linear approximation at 1 because, well, it's 1.1 and 1.1 is close to 1. Nope. What value of x would you plug in to this denominator here to get near to 1.1? Now, if you say 0.1, you would get exactly to 1.1. And I don't want exactly 1.1 because that is not a nice number to evaluate at. What a nice number to evaluate at is an integer. And so I would like to use x equals 0. So I'm looking at 1 over 1 cubed and use that to approximate something like 1 over 1.1 being cubed. Again, you're using neighboring values, nice numbers if you can. So we'll see that in just a moment. Let's go ahead and at least find the linearization of that function. So let's see. To find the linearization, which means find the equation of the tangent line, you need a point and you need a slope. Again, if you want your output to be close to 1 over 1.1 cubed, you do not want x to be 1. You want x to be 0. Again, you want that denominator to be close to 1.1, but nicer. So x equals 0 creates a very nice denominator. So I'm going to let x equals 0, and we'll look at that function at 0. Of course, that's kind of easy, right? When x is 0, that function is going to be 1. Now, the slope is a different question. We still have to evaluate the slope at 0 as well. Or, sorry, the derivative at 0. So the slope is just the derivative at 0, because that's the point we're plugging in. So we're basically finding the tangent line at 0. Let's find out what f prime is. F prime of x is going to be a negative 3 times 1 plus x to the negative 4th power times the derivative of x via the chain rule, which is just 1. And so we have a negative 3 over 1 plus x to the 4th. Well, if you evaluate this at 0, that would be negative 3 over 1 to the 4th, or negative 3. So now we have a point and a slope. We can go ahead and build the tangent line. And that would be y minus the y value for our point is equal to the slope times x minus the x value for our point. Now, obviously, in this case, I don't need to say don't distribute the negative 3 through, but I do want to kind of reiterate that you do not want to distribute through those parentheses. In this case, it actually doesn't matter, but normally you would not want to distribute through those parentheses. So this will be a negative 3x plus 1. That's our tangent line, and we are going to call that L of x for the line. So negative 3x plus 1. And now we'll go ahead and use that tangent line to approximate the value of our function near to 0. That's where we built our point. So we can only use this tangent line to approximate near to 0. If you get too far away from 0, just like we showed earlier, if you get too far away from your the place where you built your tangent line, your distance between what your tangent line is and what the true value of your function is going to widen. It's going to get worse. Not always, but generally speaking, it will. So because we centered our tangent line in this case that we're working on right now at 0, you can only approximate near to 0. So let's see, where do we want to approximate? Well, we want to get an approximate value of 1 over 1.1 cubed. And that would be f of 0.1. That's what we want to approximate. We want to approximate f of 0.1 because if you plugged a 0.1 in here, you'd have 1.1 cubed. So here we go. F of 0.1 is approximately, not exactly, but approximately the tangent line at 0.1, which is equal to a negative 3 times 0.1 plus 1. Well, that's a negative 0.3. Whoops, let me put a negative in front there. Negative 0.3 plus 1, which is a 0.7. That's pretty decent. I'm just going to grab a calculator rather than jumping into Desmos here. There's no real need to jump into Desmos. But let's see, 1 over the quantity 1.1, so 1 over, sorry, you can hear me talking to myself, 1.1 raised to the third power is going to be 0.7513. So our quick approximation to be 0.7 is pretty decent. It's not too terrible. Let's go ahead and see what else we were asked here. Use technology to determine the values of x for which the difference between our function and our tangent line, notice I already had the tangent line pre-computed, 1 minus 3x. That's just our tangent line. So compute or determine the values of x for which the distance between our given function and our approximated tangent line is accurate to within 0.1. So I want the distance between those two functions to be within 0.1 of each other. And this is usually given in a textbook with a calculator symbol next to it, so you know, oh, I have to use a calculator. So here we are in Desmos, and I'll go ahead and just graph f of x is equal to, it was 1 plus x raised to the negative third power. There it is right there. And we built our tangent line, L of x, to be, what was it, negative 3x plus 1. There we go. And I really detest the whole grid there, so I'm going to turn that grid off. Remember, this tangent line was built around x equals 0, and you could totally see that, yep, that is a distance, or sorry, that blue line is the tangent line at x equals 0. So it totally is working out. I'm going to put this in projector mode as well. Now we want the distance between those two functions to be less than 0.1. Probably the easiest way to do that is just to take their difference. I want to know when their difference is less than 0.1. I think that's what was asked. So I'm just going to graph y is equal to f of x minus L of x. And I'll turn off the other two functions. And what you're seeing here is the difference between those two functions. And I just want that difference to be less than 0.1. Well, I could just type in y equals 0.1. And now you can see all of these x values here will give me a difference. The green curve is just a difference between those two functions. All these x values will give me a difference less than 0.1 because the y values here are going to be the error. So Let's see, that's from x equals negative 0.1162 to x equals 0.1441. So I'm going to write that down. And you can see, I'm just saying for which x values is that our linear approximation accurate to our function within a value of 0.1. These x values in the interval from negative 0.1162 to 0.1441. What does that mean? It means if we're okay to have an error up to 1/10, then we can use our linear approximation, L of x, to approximate our function value as long as we're only considering x values between negative 0.1162 and 0.1441. So that is kind of a cool thing. It also lets me know that it's a decent approximation for 1 over something cubed, where that something is about a 0.89 cubed up to a 1.1441 cubed. So we get a decent approximation being within 1/10 using the linear, the tangent line. So that's a really nice example. Now, these have been kind of led a little bit. In other words, I've told you to use a function to evaluate or to approximate these, but that's not always going to be the case. And these right here are kind of my favorite examples to give on an exam or a homework or something like that, because I find that these really showcase whether a student's paying attention and that they can do these approximations using linears. So let's see, approximate the square root of 100.5 by hand. By the way, I did not have to do 100.5. I could have chosen an infinite amount of other numbers. I'm just choosing the square root of 100.5 to get my point across. So what you're going to do is first determine the base function that's being worked on here. The base function is the square root of x. So we're going to let f of x equal the square root of x. And we want to approximate f at 100.5. f at 100.5. Well, that just means I'm going to find the tangent line of this function near to that point. Now, I'm sure we all can agree that's probably going to be around 10, right? Square root of 100 is about 10, so therefore it's going to be about 10. But we can get a much more accurate approximation just by using the tangent line. Remember, the tangent line requires two pieces of information, a point and a slope. The question is, what's the point? Because then we can take the derivative and figure the slope of the point. The point here is likely going to have an x value of 100, because that's near to the 100.5 that we're taking the square root of. So I would recommend picking the point 100 comma f of 100, because those are pretty numbers, and you can easily take the square root of 100. So that would be 100 comma 10. That's our point. And so the derivative of our function at that point will be the slope of the tangent line. Let's go ahead and find the derivative of our function first. That's just going to be 1 over 2 root x. And so therefore, this is 1/20th. And 1/20th, if you don't know, is 0.05. So let's go ahead and now find the equation of the tangent line and then use that to approximate f at 100.5. So the tangent line is y minus the y value of 10 for our point is equal to the slope, which we set as 0.05, times x minus the x value for our point. And moving that 10 to the other side, we get y is equal to 0.05 times x minus 100, and then plus 10. And let's see, anything else? Oh yeah, we like to call this L of x. So L of x is equal to 0.05 times x minus 100, and then plus 10. Okay, so if we want to find or approximate f of 100.5, we could just use L of 100.5. So f of 100.5 100.5 is approximately our tangent line, but evaluated at 100.5 rather than evaluated at 100. Well, that'd be 0.05 times 100.5 minus 100 plus 10. Well, let's see. That's 0.05 times 0.5 plus 10. That's half of 0.5, which is, or 0.05, sorry, which is 0.025 plus 10, which is 10.025. That's our approximation for the square root of 100.5. Now I'm just grabbing a calculator just to find out what the actual square root of 100.5 is. And the actual square root, this is an aside, but the actual square root of 100.5 is approximately 10.024968, and then it goes on. But you can see 0.25 is a pretty darn good approximation. So this is a really neat way to do this. Again, you have to create the function in this case. And these are the types of problems that I really dig. So just to let you know, if you're one of my students, be prepared to just be handed some expression and for me to say, I need you to approximate this at this point or something like that. It could be a sine function. It could be an exponential function. It could be a radical function. It has to be a function where if I want you to approximate the value, it has to be easy to approximate nearby. So let's just spend a moment, because this is the last example I have in this specific video. So I might as well just take a moment or two to let people know the types of things they can approximate. So what can you approximate? Well, let's see. Square root of 68. That's near to the square root of 64, isn't it? It's really close to the square root of 64. So what I would do is I'd build a tangent line to f of x equals square root of x at 64. And then use that tangent line to approximate the square root of 68. What other things? Like, okay, let's stick with roots for a moment. The cube root of, let's do the cube root of 93. Well, let's see. Actually, that one's probably not the greatest. Let me do a cube root of 140. That's a little bit better. So we know that 5 cubed is 125. So I would probably approximate this using the cube root of basically like a 125, because I can easily do that. So I'm looking at y equals the cube root of x, but approximated at 125. So I'll build a tangent line to that function at 125 and use that tangent line to approximate the value of the cube root of 140. It won't be great because 125 is pretty far away from 140, but still, it can be done. Other things you could possibly approximate. Let's see. One that I'm just making up, I've never done before, but possibly like the natural log of 3. Well, that's very close to the natural log of e, right? E is 2.71828 and so on and so forth. So what you would do is you would let y equal the natural log of x, and you would build a tangent line to that at x equals e, which is actually pretty easy to do. And so when you do that, you'll get an exact value for the equation, because obviously if you take the derivative natural log, it's 1 over x, and you're using e, so that's gonna be 1 over e, which requires a calculator now that I'm thinking about it. So the moment that you have to touch a calculator, it's probably a bad approximation. So maybe this one's not that great because you would have to grab a calculator to get an approximation, and that defeats the purpose of not using a calculator, right? So what else could I do? Let's see, like a sine of 0.1, or the sine of pi minus 0.2 or something like that, because I would just evaluate the sine function in both cases at, well, in the first case at 0, or in the second case at pi. So I'm using values that I know I can evaluate a trig function at. So these are all great ways to approximate the value of functions by hand when you normally could not. There's a whole bunch of them, honestly. There's a whole bunch of possibilities. So I recommend looking at extra examples in your textbook as well, because there's just a ton of them. I'm not even looking at the textbook, so I'm sure I'm missing quite a few, but these are always fun ones to do. All right, I'm done with this video for now, so I'll see you in the next video.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.